Welcome to our Intro to Computer Vision workshop today. I will start with some general announcements, and then we'll go on to our workshop and talk a little bit about computer vision, and we'll introduce some functions, and we'll explain a little bit about how it's used in real life. So just a reminder to pay your dues. You can pay online by going to the UTSA ACM website under the tab Join. It's $20, and this makes you eligible to get an ACM shirt and eligible for the drawings that we have towards the end of the semester. I believe some of the drawings include a 3D printer. We have swag and stickers as well. So make sure to pay your dues. You can also scan the QR code we have provided here, and it will direct you to the ACM website. If you have any general questions, you can ask them in the Slido, or you can type them in the live YouTube chat. We will be answering them through there as well. Make sure to join our social media platforms to stay up to date on all the events we have going on every week. We're on almost every social media platform out there, but our main one that we use for communication is Slack. Our upcoming events, ACM-W will have their meeting Tuesday, November 3rd, and they'll be featuring day in the life of a data scientist. So make sure to attend. We have our general ACM meeting on Wednesday. The topic will be digital sustainability, adoption of autonomous systems in smart cities. This will be Dell, so make sure to attend Wednesday, November 4th. ICPC will have their general Saturday meeting, November 7th, and this is actually their first contest. If you attend, they'll be raffling Amazon gift cards, and their meeting is very newcomer friendly as well. This will be November 7th at 10 a.m. until 1 p.m. Rowdy Creators will also have their November 1st meeting. It takes place on Sunday from 3 to 5. If you have a project idea that you want to go about, please talk to them. They can help you bring that idea to life. You can join their Discord channel by clicking on this QR code right here we have provided. Okay, so we will start our workshop. Okay, so computer vision is an artificial intelligence technology that allows computers to understand and label images. What it does is it helps computers see and understand content of a digital image. It tries to imitate human vision. Some examples of real life that use computer vision are the self-driving cars. They identify obstacles and avoid collisions and accidents. They also use computer vision to create 3D maps of the surrounding areas to spot obstacles and to have an idea of the path. For home intruder detection and drone camera surveillance, computer vision is used to identify objects, moving objects, to identify faces, and to identify just different objects for intruder detection and surveillance. In the example we have here in our poster, as you see on the right, the people are of color pink. This is thanks to instance segmentation that identifies the boundaries of objects and is able to identify the different objects based on their pixels. So how do computers see images? So images can either be inputted, or it can get the images directly from the camera on the computer. A video is processed as a series of images. So a video is broken down into, for example, 60 frames per second, and that's how it's able to process a video as opposed to an image. Pixels are the smallest element of an image, and every pixel has its unique values. The standard color channels are RGB, and every pixel has its unique values, and that's how it's able to differ from different objects. So we have three ways of representing colors. One of them is RGB, or BRG in Open Computer Vision. So there's in this channel, there's three different colors: red, green, and blue. And the image is represented by getting the values, the different values from these. We have HSV, which is hue saturation value. And this also has three different values. And what this function would do here, CV2.color, it would display the image in color. For grayscale, grayscale only has one color, only one value. For example, black to white. And what this command here would do, it would display the image in a grayscale. We have a link that we're going to show you. So we have we're using rapid tables, and with this website, you can see how the different values of RGB change as we move through the spectrum. It also shows you the different hue and saturation values as we move through the spectrum. It also has the hexa number, but in Python we would use the RGB value. So OpenCV Python is a library of Python bindings designed to solve computer vision programs. It's referred to as OpenCV Python documentation. And the way that you install it is by installing an IDE. And in a demo that we will be doing, we'll be using Spider. But there's a lot of other IDEs out there. And by running this line right here, you would make sure to install the computer vision library that you would need for computer vision. Or another option is that you can use the Google Colab notebooks. It's an app in Google already. So this app already has the OpenCV library, so you wouldn't have to download any extra stuff. It's really convenient, and you can access it by going to your drive. And also, to make sure that it's installed, you could run this line, import CVC2, CVC2.version, to make sure that you have that library installed. Okay, so for getting images to your program, we have a few functions here that we want to explain. So what capture.cv2.video does is it lets you create a video capture object, which is helpful to capture video through the webcam. what the zero represents is the source. It kind of depends what you're using, if you're using your camera from your laptop or if you have an external camera, what this number would be. But by default, if we're using a camera from a laptop, it would be 0. But if you're using an external camera, you could trial and error between 1 and 2. But by default, it would be 0. What NetFrame does is it captures the frame, it captures by frame to get input from the connection. And you always have to release the connection. If not, you would have an error at the end. So this is what this function does. As opposed to a static image, you would have to use this function. And inside the parentheses, you would have the file path of that image. That file path is where it's located in your computer, whether it's the downloads or desktop. And that would allow an image from the file path to load. Okay, so these are some other basic OpenCV functions. So what this first one does, cv2.imshow, is a method used to display an image in a window. The window will automatically fit to the size of the image, and you would input the string name of the pop-up window and the video or image. And the name of the window is a string representing the name of the windows. And what window normal does, it sets the resolution and the size. And it's helpful because it's often common to have more than one window open. So if you name the window, you have a more clear vision of what you're looking at. And what close all windows does is it destroys all windows and closes them all. So that's pretty straightforward. And sorry, I missed one. Resize the window. You can just change the length and height of the window, and then you would specify which window you're making those changes to. Okay, so there's different tasks within computer vision. These are classification and localization, semantic segmentation, object detection, and instance segmentation. So the goal of semantic segmentation, the first one we have here, is to label each pixel of an image with a corresponding class of what is being represented. So ideally, the classes would be predefined in this one. The second one we have here is classification and localization. So image classification involves assigning a class label to an image, and localization is drawing a boundary box around the object of the image. So as you can see here, we have a box drawn around the boundary of the object, and we have our class labeled cat. Object detection locates the presence of objects with the boundary box as well, and it recognizes the classes or the types of the located objects in an image. So as you see here, it was able to locate three different objects, and label the class. With instance segmentation, it identifies the boundaries of the objects by analyzing the pixel level of each. So as you can see here, each one of these is of a different color, and it's labeled. And each one of them is a separate object. It's clearly defined with a boundary. The difference between semantic segmentation and instance segmentation, the first one and our last one, is that semantic segmentation is pixel level classification, while instance segmentation uses an object detection step to obtain each instance, each one of these objects of all the classes in the image as a whole. For example, if these were people, it would say person 1, person 2, person 3, person 4, and semantic segmentation would just label the whole group as person 1. Okay, so color segmentation using OpenCV. So for this, we would be using masks. So what mask is a layer on top of an original image that will cover certain parts of the image. For example, if the area of interest is white, all the other areas will be black. With a mask, what we can do is find specific colors and completely isolate those specific colors from the image. As you can see here, we had a picture in color in RGB, and then we changed it to grayscale. We were able to isolate with a mask those specific colors and only show black and white. So for masking colors, we would use a function in our library. So we would use an array to define our lower bounds and upper bounds. For example, right here with this function, we put our low bound and our high bound, and inside of the values here, we would specify which values we want to mask. If we wanted all red, we would put high red, low red, and we would only have those red colors showing. This is one way to do it, and then we can also we also have another example here of what the array would look like. And once we have those boundary set, those boundary of colors, the upper and the lower, we would create our mask with an OpenCV function. And with this function in range, we would take those boundaries and apply it to our image that we want. And then we would assign that to our function. And that would finish creating that mask that we want on an image or a video. Okay, and I will pass it back to Janelle. She will explain a little bit more about the concept of masks.
Yeah, so just to wrap up with what we went over with masks, I want to make sure that everybody understands that a mask, it's not changing the original image. It is creating a new layer. So each time we use the in-range function to make a mask, what we're doing is we're creating this new image, whereas we still have our other one constant. So like Vanessa was saying earlier, we took a color image and we said we want to mask everything except for the green. So a bunch of the green is white, and then like we can see the dog doesn't have any green, so it's all black. But these are two separate images. They don't affect each other. So we showed how to do this color masking where we can get the color that we want to isolate to be white in our mask and everything else is black. But how do we make our color show through? So in that picture of the dog, let's say we want to make the green show through instead of just having it be white. For this, we can use another OpenCV function. It's called bitwise and so it looks like this, and what it takes as its arguments, at least for our purposes, is going to be the input image twice and then the mask. And you might be saying, why are we putting the input image in twice? And that's because usually bitwise and is used to compare two sources. So the image here and then the image here. But we want to compare this source to a mask. So we'll just use the same source in both of our two sources, and then we'll put in our mask and we'll compare it to that. And what the result of this bitwise and will be is that everywhere that is white or is, I guess we could call it on, so everywhere where the pixel value is 255, where it's white, is going to be an area where the color in this original input image shows through. And we'll go through this in a demo so you can see exactly what this looks like. But just the idea is that anywhere in the mask that's white is considered on, and anywhere that is black is considered off. So it'll show where all of the input image is on. So now that we've done a little bit of our segmentation, just going pixel by pixel, seeing what color it is, we might want to localize these colors or draw a bounding box around where these colors are. And so how we can do this is we can use the contours that are in our mask. So the reason why we use the mask is because the mask is just a black and white image, right? And so the difference between the black and the white is a lot because black, as Vanessa was talking about, in the color channels, black is 0 and white is 255. And so that's a very stark difference. So it makes it very easy to find different lines from that mask because it's such a big difference. So we'll find these contours that way. And then for each contour, we're going to check and make sure, okay, is this a significant size? So for example, if we're looking for green in this cat image instead of the cat, do we want to go by like every little tiny blade of grass, or do we want to just circle like the whole area that's green, or maybe we get some green noise back here. And so it's important to make sure that it's going to be a significant size. And then from that, we can find the boundaries of the contours. So we'll go over this in an example in codes coming up. I just kind of want to give you like an overview. So first we're going to see if they're a specific size, or at least a significant size, and then we're going to find the boundaries around these contours. And based on that, we'll make a rectangle and we'll put text to label it. So it'll come out looking something like this, but instead of an object like a cat, we will label different colors. So I mentioned that we need to find the contours to start off because this is how we're going to localize or draw a bounding box around our colors. So OpenCV has a function for this. It's called find contours. And you'll notice that it returns a couple things. It returns contours and then something else. This is a hierarchy of those contours. We're not going to worry about that right now. We're just going to keep it simple. So right now we just want to get the contours. And so what we'll do is we'll use our mask because, like I said, it's a very stark difference between black and white. So we know right where those edges are. And then the second argument, what this does is it tells the computer how to compute the relationship between these contours. And so this gets back to what I was saying with it returns like a hierarchy or a relationship between contours. So one might be more important than the other, but we're not going to worry about that. So we'll just use something that is pretty default. which is this return list. So it'll return a list of the hierarchy. And then this last argument is how the contours are going to be saved. So if we find contours, and let's say we're finding the contours of this white box, if we find these contours, it saves every single point on this line, which would be a lot, especially when we're talking pixel values. And so to make it not save as many points, what we'll do is we'll use this chain approx simple, and this will eliminate any insignificant or redundant points to just make it more clean and make sure what we're saving isn't going to be all of these little points. We might just save the corners or something like that. So we still get the contour, but this last argument, what it does is it just makes it more simple. And so this is how we find the contours. The really important things from this are just to use the mask, because again, black and white is very different. So it's easy to tell contours. And then this last argument, which is telling it to just save the simple version of the contours. Don't save every single point. So once we have our contours, we can go through all of them and we can see if the area that the contour contains is significant. So what I mean by that is you might have a contour that's like a very, very small circle. And we don't necessarily want to label that because it's not, let's say if we're classifying color or we're localizing color, that's not a big area of color. So what we'll do is we will get the area of these contours, and OpenCV has a function for this too. And it's just called contour area. And so what we'll do is we will just pass it the name of our contour from our previous function that we got, and this will be our area. And we can say if the area is greater than some minimum value. So for example, in our demo, we'll do if it's greater than 400 pixels, then we'll go ahead and consider it, and we'll draw a rectangle around it. So if we're going to draw a rectangle around it to localize it, how do we do this? Well, first, we can get to the rectangle that goes around our contour by using this function from OpenCV called bounding rect. And we pass it the name of our contour, and what it will give us is the x and y coordinate of the top left point of the rectangle around the contour. And it will also give us the width and the height. So this gives us everything we need to draw a rectangle, because we know where it starts in the top left corner, and we also know how wide and how tall it is, so we can use that to draw a rectangle around this contour. So the last two steps, they're not very specific to computer vision. This is just drawing a rectangle and putting some text on the screen. So we'll use another OpenCV function called rectangle, and we'll pass it what we want the rectangle to be drawn on. And then the top left coordinates, both x and y, which we got from this boundaries. And then the bottom right x and y, which we can get by adding this top left x plus the width, and the top right y, or top left y plus the height. And that will get us our bottom right and bottom left, or bottom right x and y. And then the last two are just stylistic choices. So what color you want to make your rectangle. This is in BGR because it's OpenCV. Normally we have the color channel RGB, like Vanessa was saying, but we kind of reverse the order for OpenCV. And then the thickness. So that's just another stylistic choice. So the last thing to do is to label the rectangle. So what are we localizing? What are we looking at? And again, we'll just pass it arguments like what we want to put the text on, the text, the top left x and y coordinates, and then we'll specify some stylistic things again, like font, how big is the font, what color is it, and then how thick is it. So what this will end up looking like if we do all these steps that I just went over, and don't worry, these will be in the demo. So if you're like, I didn't catch all of that, we're going to go through it again. But what this will look like is it'll draw a bounding box over what color you're looking for. So let's say we were looking for blue and we used a mask of this. this is what it would look like. We would have a white box, and here's our text we put with it, blue, and so it's very clear what that is to us. So now we're going to get to see all of this in action with a demo. So as Vanessa mentioned, you can use Spider or any like Python IDE, and you just need to install the OpenCV library. So let's go ahead and make sure that the OpenCV library is installed on my computer. So we can say import CV2, which CV2 is the name of the OpenCV library. And then what we can do is we can print the version to make sure that it's installed. So this is what Vanessa went over, but we'll just run this to make sure everything's fine here. And we can see down on our terminal or our command line that we have 4.2.0. So that's perfect. That tells us we have OpenCV. It's version 4.2.0. And so we are ready to go. So the first thing that Vanessa talked about was how to get an image or a video into your program. And she talked about a function that OpenCV has, or it's a class that OpenCV has, and it's called video capture. And we mentioned that the 0, this will come from me. I'm on a laptop. So the default source or the 0 source for images is going to be my computer. And this is very important because right now, so I'm on Zoom, you can see my face. And so that means that the camera is being used by Zoom right now. So I'm gonna go ahead and turn off my video camera just to use it for the demo instead. And so if I set up this connection here using the video capture class, I'll create an object of this class called cap. And this is what we're going to be using this object to read in our video. And so since it's a video, what we want to be doing is, like Vanessa said, it's just a series of these images. So we need to keep reading from our video stream, in my case on my laptop. So I'll go ahead and create a loop. I'll just say while true. What I want to do during this loop is I want to read from this capture object or from my webcam. And so what this function returns is it'll return a return value saying if it worked or not, and then the frame that gets captured. So this frame will just be an image that comes from my webcam. And so we don't want to make this an infinite loop. So let's go ahead and establish an exit condition here. And so what we'll do is we'll have it break on a certain key. So OpenCV also has functions like wait key. And that means that if a certain key is pressed, you can do something. So it'll wait for a certain key to be pressed. In our case, 27 means it will wait for the escape key, and then we'll go ahead and break out of this loop. And so just to make sure this is working, we will show what our camera is reading in, or what our program is reading in from our camera. So we'll use another OpenCV function called imshow, and we can title our pop-up window. We'll just call it frame, and it's going to show the frame. And so this is to get the input from our camera, this is to show it, and this is our exit condition. But we have nothing that says once we're done, give the camera back to our computer, to our other programs to use. So like Vanessa said, we'll use another function of the capture object called release. So this will give our camera back. And then also, like Vanessa went over, we want to close this frame, this window that we have popping up called frame. So we'll use another OpenCV function that is cv2.destroy all windows. So this is the portion of the presentation that was just at the very start, very basic OpenCV, where we are just getting a video and we're getting ready to show it. So let's go ahead and see what this will look like. So I just clicked run, and then you'll see it comes up in this little file over here, and you can see me. It's called frame. And if like I move around, if I wave, it's constantly reading from that loop. So it will pick up what I do. So I'm going to go ahead and exit this so we can get back to writing our program. And I'm going to use the escape key to do that. So that worked perfectly. So now we saw me, regular color. Let's see how we can use some of those color channels that Vanessa was talking about to make some changes. So we'll go ahead. And she talked about hue, saturation, value. Those are 3 color channels. So let's go ahead and convert this regular frame that I have to hue, saturation, value. So we will use the convert color function in OpenCV. And the first argument is going to be like the input image. So in that case, in our case, it's the frame because I saved my camera input as frame. And then it's going to want to know what color we want to convert it to. So we'll use CV2 color underscore BGR. And you'll see it's already popping up with a lot because these are just in the OpenCV library. But we'll do BGR to HSV. And like I said, this is not going to affect the original frame. This is going to affect, or it's going to be saved as almost like a new layer. So we need to save it like that. So we'll assign it to HSV frame. All right, so here we have converted it to HSV. And so let's do the same thing we did with our original frame. We'll go ahead and show it. So cv2.imshow. This is honestly your best friend. If you learn one thing from here, learn how to use imshow because we'll be using it a lot in this demo. And so we'll go ahead and show the HSV frame and we'll just call our window, let's just call it HSV. So if we go ahead and run this, then we can see now there's normal me, and then there's hue, saturation, value me. So it's converted the colors. We'll do one more just to say we did. We'll convert it to gray. So we'll say gray frame equals cv2.convert color. And we will take our original frame again because it's not been changed. All we've done is we have just created this new HSV layer. So we'll take our original frame and we'll do cv2.color. Again, from BGR, because that's the default color channel, but this time we'll go to gray. And we'll show it again using cv2.imshow. And we'll show our gray frame. So here's all 3 of me. We have our original RGB, gray, and HSV. All right, so that is how you can mess with the colors a little bit. It's a little bit fun and just takes a couple lines of code to do. So we'll go ahead and continue on. The next part of the presentation we got to was masking. So this is really what we're going to be focusing on. So we want to make a mask, and let's say that we want to mask all of the values that are not blue. So we just want to show something that's blue because my room doesn't have a lot of blue, so it'll be easy to kind of wave objects in front of and show you guys how it can show blue. So what we're going to do is we're going to use the function Vanessa was talking about, which is inRange. And we will feed it a input like image or video. So in this case, it would be one of these frames that we've created. And then we also need to give it a lower bound and an upper bound. And it says right here, again, the source, lower bound, upper bound. So how are we going to decide our lower bound and our upper bound? Well, let's do it in HSV. So we're looking for blue, right? And so if we go to our rapid tables color picker, then what we can do is we can go down to the border of like blue and purple. So this is kind of purple, but just for starting, we'll go with it. It's right on the border. And so you'll notice it gives us the hue, saturation, and value. But this one, I'm going to have to do a little bit of conversion because you'll notice in OpenCV, our hue, saturation, and value are values out of 255. Whereas here we have our hue. If we go up to red, it goes up to 360. So if we want to get like 270, I'll go ahead and convert it and make it out of 255 instead of 360. So 270 out of 360 is equal to about 190 out of 255. So that's our H value. So we can go back to our program and we need to create this lower blue and this upper blue. And these are both going to be NumPy arrays. So we'll need to import NumPy and we'll do np.array and we'll create our array. And we'll do the same thing for our upper bound. So we said that the first one, I did the calculations. We said it was about 190. All right, so let's see if that was our lower or upper. So by sliding the scale, does the blue value, or does the H value for blue go up or down? So it goes down. So that was our upper bound. That was the H value for our upper bound. So we will put 190 in here. And let's go ahead and find the H value for our lower bound. All right, we're about at like 170 out of 360. So again, I'll just calculate that and make it out of 255 instead. So we get about 120 out of 255 for our upper bound, or for our lower bound, sorry, I switched these. So we'll make this 190. All right, so we have our H values. We're not going to spend as much time on the saturation and value. These are in percents. So I'm kind of just going to have to guess here. So if we go down towards black, we get around like 25%, 40%. It starts to become pretty black. So we'll just say we don't want a very low value. And this is where kind of like guesstimation and trial and error comes in. Of course, you can be more precise with this, but I'm just going to let my saturation and value go up to the brightest colors. So we'll just say 255. And I want it to be able to detect dark blue, but not too dark. So let's say like 25 for each of these. All right, so that was a lot, but we have our lower and upper bounds. So what we can do now, since these are in HSV, we are going to use our HSV frame. And our lower bound is called lower blue, and our upper bound is called upper blue. And we're going to find the colors in that range, and we are going to save them to a mask. So we'll say mask except blue. All right, and so let's go ahead and we'll see what this gives us. So we'll do cv2.imshow. We'll say show blue and mask except blue. All right, that looks good. So we'll go ahead and run this and see what it gives us. All right, so it doesn't show any blue. There's not much blue in my room. We can kind of get rid of some of these. but it's not picking up really anything. If I show this water bottle, it kind of picks up some of it, but it's not doing a very good job. So we can go back and change our arrays that we have. So I want to make it easier for something to be blue. So I'll go ahead and remove this lower bound. And if I run it, then you can see now it's kind of picking up some of the blue in the background. And now it's picking up this water bottle better. So try to trial and error it. You can always stick to and start with the color pickers, but to create our mask, you can also be a little bit flexible and just see what's working and what's not and play around with it. So that's great. We have our blue mask, but what if we want, instead of the things that are blue, they're appearing as white right now. What if we want them to appear as blue? So we'll go to that function that I talked about, which is bitwise and. So we want now to mask everything except for blue, but we want it to be in color. So we'll use bitwise and what this does is, again, I said it takes two sources and it'll compare those. But we're giving it two sources and a mask. So we want the sources to be the same so that we only compare to the mask. So we'll give it both the original frame and we will give it the mask that we created. So we'll say mask equals mask except blue. And so wherever this mask except blue is white, or where it's on, it will let that blue color show through. So we'll go ahead and show the effects of this. Again, using imshow, we'll say show blue color, and we'll say mask except blue color. So if we run this now, and I hold up this blue water bottle, we can see where it says show blue color. This was our bitwise and then our show blue made everything in blue white, but now instead we see the original color peeking through. So that's the power of bitwise and, is it can compare two different sources and whatever is quote unquote on. So in this case, in our mask, white is on and black is off. It'll show through. All right, so now we have our blue. We've done a good job with that. What about the second part of the presentation where we localize colors? So what localize means is we're going to draw a bounding box around it and we're going to see where it's at. So I can actually get rid of some of these. We didn't use the gray at all. That was just to show all of you. But what we're going to do now is we're going to find those contours. So the outline of all of the blue area. So we'll use, like I said, the function find contours. And we want to put in our mask. And so, like I said, when we find contours, it's easy to make a distinction between black and white. So we'll use our black and white mask, which is this first mask except to blue, that does not use the bitwise and, to find these edges. And so the second and third, like I said, are how these contours are going to be stored. We're not worried about the hierarchy, so we're not going to be worried about the second parameter, but we want it to be stored simple. We don't want all of the different unnecessary points being in there, and so we will pass in chain approx simple for the last argument. And this is pretty common, but you can look up on the documentation more about what this does. And so this find contours function is going to return two values. It's going to return the contours and, like I said, the hierarchy of contours, but we're not really concerned about that. So we'll just save it in some variable and we're not going to use it, but that's all right. So let's see kind of what these contours look like. What do I mean by drawing contours around things? So we'll use this function in OpenCV called draw contours. And we need to pass it what it's going to draw the contours on, so the frame. We also need to pass it the contours that it needs to draw on, or needs to be drawn, which we use find contours to find. And then -1 means we want it to draw all of the contours. And then we'll give it a color to draw them in. So let's say green. BGR will draw the contours in green, and we'll draw them 3 thick. This isn't really all that important. I just want to show you what the contours look like, so you have a visualization of that. So we'll go ahead and show, we drew them on the original frame. This is changing our frame. So we'll show our frame again, and we'll see what our contours look like. So if I bring this over, this is our contours. You can see there are all these green little dots, but if I bring in my water bottle again, you can see that it more or less outlines the water bottle. So that's what we mean by contours, and that's what those are, is those are just the edges that we're drawing there. So for every contour that we saved, so every contour in contours, because this is a list of our different contours that it saved. We had some in the lower left corner, we had some around the water bottle, so there's multiple. Like I said, we need to find the area. So we'll use an OpenCV function called contour area to find those. And we will find the area of, we'll pass it the contour we're currently on. So maybe it's one of the contours that made up something that was surrounding the water bottle. So we'll say if all of those green dots around each other, we'll take that area, and then we'll say if that area is greater than, let's say, 400 pixels. And then we'll go ahead and draw the bounding box. So how we draw the bounding box is we use this cv2.bounding rec, and we'll pass it the contour, because what this function does, again, it will take this contour and just give the coordinates, the x, y, width, and height of a rectangle around those contours. So we pass it the contour, and it returns us these points that we can use to draw our rectangle. So the very last thing we're going to do is we're just going to draw a rectangle, and we're going to add our text describing what our rectangle is. So we'll do cv2.rectangle, and we'll draw it on the original frame that just has me in regular color. We'll start our rectangle at the XY in the top left, and then we will end it in the bottom right with our x plus width coordinate, and our y plus height coordinate. And then let's just make this, let's make the rectangle blue, because we're tracking blue. So that's BGR, so a lot of blue, no red, no green will give us blue. And then the thickness of this rectangle, we'll just set it to be 3. And so this is going to return a rectangle with this. So we'll just save it as box. And then we're just going to put text on, and we will be done. So we'll say put text frame. Again, we're putting it just on the original image of me, and we're tracking blue. So we'll just say this is blue. And we'll put it in the top left corner of the rectangle we're drawing. So we'll start it at this XY. And the rest is just stylistic things. So it's just the font, and OpenCV has those already. So no need to worry there. Just pick one that you'll like, or hit tab until it gives you a font. This is the scale of the font. So we'll do 1.5 just so you all can see it. And then this is the color of the font, so we'll make it white. And the very last thing is the size. And since we did such a big scale, we'll just keep it normal size. So that is for localizing. And so we drew it on this frame. So we'll go ahead and show the frame again at the end. And if we run it, then we can see in this little contours that it's starting to show up with this is blue, and it just takes my water bottle. So we have created a mask with this color. So we've done some like semantics, and we've done some segmentation by pixel, and we've also localized it with this bounding box. So this is just an intro to OpenCV. I hope that demo kind of helped you visualize some of these topics. And yeah, it wasn't too bad code-wise either. It was, I think, less than maybe 40 lines of code to do it all. And so now we're going to go back to our presentation and wrap up. Again, if you have questions, feel free to put them in the YouTube chat or the Slido, and we'll get to those right after this. So what else can you do now that you know what we've taught you in this workshop? So one thing you can try to look up and find how to do is see how you can get rid of some of the noise. So you notice in the mask that we had some areas in the bottom left and the bottom right that were saying that they were blue. Can you find a way to kind of smooth that out and make it more accurate? You can also try it with different colors or multiple colors. And you can also take this beyond colors and try to do things like classify and localize objects. And there's just a lot more you can do. So I highly recommend that you check out the documentation to kind of see more of that. But from there, is there any, let's see if there's any questions in our Slido.
I don't see any questions on the YouTube either. But is there like a resource that you would point us to if we wanted to learn a little bit more about computer vision?
Yeah, so I would definitely say the best place to kind of just look around and see what's offered. You could look in the documentation to see more what you could do. But if you want something that's more like beginner friendly, there are tons of tutorial videos out there on YouTube. If you just search like OpenCV like color masking, or there's also different blog posts. So Python is really good there's a lot of different blog posts in that community. So if you go to the blog posts, then you can see people work through problems of their own. And even some of the documentation has some like sample code and sample problems. So definitely just get out there, start Googling, looking up YouTube videos about this sort of stuff. But yeah.
All right. Thank you, Janelle. That was a really good presentation and really good demo. Thank you for that.
Yeah, no, thanks, Vanessa. Appreciate it. We make a good team.
Okay, I don't think we have any more questions. I don't see any on the Slido or the YouTube chat.
Yeah, all right. So I guess we'll go ahead and wrap it up. Yeah, so thanks, Vanessa, for giving that intro on all of like the basic functions and everything. And then we had our demo, and so hopefully you guys learned a little bit about OpenCV from that. But just to reiterate, we do have some upcoming events for ACM. So the next thing is going to be next Tuesday, not tomorrow, where ACM-W has their day in the life of the data science, or a day in the life of a data scientist. And then we have our ACM meeting the day after, so Wednesday, November 4th, about digital sustainability. And this is going to be talking about smart cities. But before both of those, we do always have ICPC on Saturdays. They'll just be practicing this Saturday. But next Saturday, they do have a contest. So go ahead and scan that QR code link. If you want to get more info on that, that'll take you to their Discord where they have a contest info channel. And there will be prizes for first place. And so it's no stress if you lose. It's just a very local competition. But there is some prizes out there for you if you win. So definitely go and try that out. And then on Sunday, we have Rowdy Creators. And I highly encourage you go to those because that's actually where I learned about OpenCV. So you can learn some of these skills and create new projects with that. And their Discord is linked in the QR code. And with that, I think I'll leave up this slide. But thank you all so much for coming and have a good rest of your night.